Today we'll discuss one of the most important topic of the organic chemistry, and that is reagents. Okay. Here, let's start from the scratch, because the entire understanding of organic chemistry depends on understanding of reagents. If you understand reagents, you can understand everything. You will enjoy organic chemistry. Okay, that's why you need to be more careful and more attention is required, right? Fine. What is resonance? Resonance is delocalization of pi electrons. Very simple definition. What you say? You say that resonance is delocalization of pi electrons. Delocalization of pi electrons. Just simple definition, right? Let's understand this one. There are a few terms. One is delocalization. What do you mean by delocalization? Delocalization means which cannot be identified or characterized with location. Sometimes here, sometimes there, which keeps on changing its place. That is delocalized. So meaning is very clear. Delocalization. It is clear. Then which electrons delocalize? Very natural answer. Electrons are very tightly held by, in general, electrons are very tightly held by the respective nucleus. So which electrons will move? Electrons which are loosely held. Which are those electrons? Pi electrons. What do you mean by pi electrons? What do you mean by pi electrons? Pi electrons, sir, electrons present in pi bonds? This is correct, but very limited one, right? Here, pi electrons means electrons present in unhybridized orbitals. Unhybridized orbitals. Okay, understand this one? Unhybridized orbitals. These unhybridized orbitals also called pi orbitals, right? Called pi orbitals. Then immediately you can think that, sir, what about my definition, sir? Because I think that electrons present in pi bond. You tell me one thing. Which orbitals form pi bonds? Yes, sir, yes, sir, yes. Unhybridized orbitals form pi bonds. Unhybridized orbitals form pi bonds. Yes, that only I say. Here, unhybridized orbitals are called pi orbitals. Electrons present in unhybridized orbitals are pi electrons. Where we will find those pi electrons? Those unhybridized orbitals. Yes. There are the few cases very defined. All kind of resonance you can keep in these four categories, right? Here, and I just give the example also, right? Because I want to simplify this one. Here, You see. There the delocalization of pi bonded electrons with pi bonded electrons with the pi bond. This is the first one, pi. In this category, you can see, I just write one example, okay? That CH2 double bond CH double bond CH2 double bond CH double bond CH2. Here you try to understand this one, that in this case there is resonance, there is delocalization of pi electrons present in this pi bond with that pi bond, or electrons present in that one with this pi bond. How? Here you understand that this pi bond electrons, as I said there, that loosely held electrons, so can move, can change its place, right? Then you can ask me one thing, that why that is changing its place? That is changing its place because that is a kind of, that is dispersion of electrons. If electrons are localized, that is reactive. Delocalized, more dispersion, lowering of energy, increasing of stability, right? So that imparts greater stability to that one. So this is a kind of stabilizing phenomenon, right? Here, these two electrons which are present, you may find like this. What is the meaning of this arrow? Meaning of this arrow, this electron is already with this carbon atom, and this electron of that carbon atom also coming with this carbon atom and getting accumulated over this carbon atom. So when we break this one, this is a kind of heterolytic cleavage. This will be having negative charge, this will be having positive charge. Why negative charge? Because this bonded electron will be there now with this carbon atom. This is one extra electron. And this one is losing one electron, that's a positive charge. So you will write here, okay, CH2 and their negative charge, and here you write positive charge, and that time you don't disturb this pi bond. Their pi bond breaks down and that is getting accumulated. This is also one of the electronic arrangement. And here negative, there positive. This has now vacant orbital. So you understand its hybridization is sp2. This one is the pi orbital, unhybridized orbital. So now in this orbital, this electron, right, this carbon is taking both the electrons and giving to this one. Here the two electrons. These two electrons are given to this one. One electron is certainly of this carbon atom, other electron of that carbon atom. This carbon is taking even that electron and just giving to this one and sharing with this one. This one is shifting of electrons. I have indicated in the middle of this one, means electrons are shifted from that direction to this direction. This arrow indicates accumulation of electron and this arrow indicates shifting of electrons. Okay. What do you write here as a result of this one? As a result of this one, you write CH2 minus, and here as electrons are shared with this one, so no more positive charge because double bond forms no. And this carbon atom is losing one electron, so this will be having positive charge. In this way, here this kind of shifting of electrons start, and that pi bond participates in this process, and due to this, here you now find negative charge, there you find positive charge. Electrons start moving. It is not reaction, it is internal. Their possibility that how you stay in your that house, from one room to other room to other room. So that is a possibility, and all these things are happening, right? This is happening, that is happening. These are the various possibilities, right? We express all those possibilities with these various electronic elements. Are you getting this point? Again, it's not like that it is fixed. It keeps on happening, right? So again, you will find that this negative charge, 2 electrons are there. This will be coming here. How it can come to this place? This has already 4 bonds. Will come. When this will come here, this pi bond will move there. And again, this pi bond is shifted in between this carbon and that carbon. And that is possible because this carbon atom is having vacant orbital. This is the pi orbital. This is the vacant one. This can take this bonded pair of electrons, and in that way the charge is nullified. Again, it will be back to this previous structure. Again, from there to here, here to there, all these things are happening. If this molecule is there, it means you think that all these things are happening, and here all these are the characteristics. Whatever you think for this one, that is there. Whatever you think for this one, all those things are there. I will come to this point later, that what is the meaning of, what is the significance of these various structures. We'll come on, we will take this one very seriously. This is the first kind of delocalization of pi bonded electrons with the pi bond. I take here the other one, okay? I take here the other one, that is here delocalization of pi bonded electrons, pi bonded electrons with pi orbital, containing no electrons. Pi orbital is there, but electrons are not there. Yes, that's why I said, when you are saying that the pi electrons, resonance means delocalization of pi electrons, and pi electrons means, if you say electrons present in the pi bond, that is not enough. That is just the first case. But now in this case we see, yes, delocalization is possible, resonance is possible with one of the orbital which has no electrons. We say that one pi orbital and containing no electrons. This is also one of the conditions. Example, yes, you take the example. Here Very simple example I say CH2 double bond there the CH in CH2 plus. You tell me what is the hybridization of this carbon? Certainly this one is sp2 hybridized. If sp2 hybridized, it means it has one of the unhybridized orbital. This has no electron. It is available to accept, to share electrons, and that is happening. That is happening. You see. Up now, there is pi bond. So here these pi bonded electrons will move towards this one. Will go there. This carbon is taking here these two electrons and taking from this one, giving to that one, sharing with that one. And as a result of this, what do you write? As a result of this, you write now, as these two electrons are shifted. So this one is now CH2 plus. This one is losing electrons now. And CH double bond CH2. Yes. You write like this. This is also a kind of delocalization. This is also regions. Right? So this is also one of the category where you find you observe delocalization of pi bonded electrons with pi orbital containing no electrons. You will see the other kind also. Right? What is the next? Delocalization of pi bonded electrons. Delocalization of pi bonded electrons with pi orbital containing one electron. When we say pi orbital containing one electron, immediately you will recall, oh, radicals, free radicals. We say radicals. Example, just you take one example. Here we write CH2 double bond CH in CH2 dot. This has one unpaired electron. What is its hybridization? Hybridization is sp2. Where is this unpaired electron? Unpaired electron is present in unhybridized orbital, pi orbital. That pi orbital contains one electron. Now, here, what happens in this case? Here, one electron is moving. In this case, half arrow we indicate because this orbital contains already one electron. It will accommodate only one electron. So this carbon is taking its own electron and sharing with that carbon atom. So in that way, the one of the electron is left here. Of this bond, one of the electron is left. And as a result of this, what do you write? You write here CH2. One electron is left. So that is there with this one. And this electron is now shared with that one. So forming a new pi bond here. CH2. That is resonance. Right? That is delocalization. So, in this kind of situation also, we observe delocalization, and this is also resonance, a kind of resonance. I give one more condition, right? I give here one more condition, right? You see. That one is, now I hope you understood this fourth one. Delocalization of pi bonded electrons with pi orbital having 2 electrons. 2 electrons. Understand this? Here you see I write here CH3 CH2 CH2 minus. If you write CH3 CH2 minus, its hybridization is sp3. sp3 hybridized. This is carbanium, negative charge now. This one is carbanium, and this one is sp3 hybridized. But when this is present here adjacent to sp2, the same carbanium or the atom with lone pair of electrons. The negative charge means what? Negative charge means 2 electrons are present. Negative charge means 2 electrons, but only 1 extra electron. So, in this situation, when there is sp2 hybridized carbon atom on the adjacent one, then its hybridization is also changed. And now in this situation you will say this one is sp2. It's not like some special condition it is happening here. It is not like this. It is a general rule, and you know what rules you have learned in the chemical bonding. For the prediction of hybridization, no rule will help you to find this kind of hybridization. Right? This is 100% conceptual understanding of hybridization. You have to understand that what is the purpose and how this is affecting their hybridization also. Here, these orbitals are changing its hybridization because it prefers to be present in unhybridized orbital. Being present in unhybridized orbital, that can undergo delocalization, can assume greater stability, and for the stability only all these things are happening. Yes, here only no. Many places we have. Here you see, what is the hybridization of this carbon atom? When we say there, what is the hybridization of this carbon atom? Where their negative charge? This one is sp2. sp2 hybridization. But if you write like this, their negative charge, yes, this one is sp3. On the adjacent place, there is sp2, so it prefers to keep this electron pair in unhybridized orbital, so this can move. Electrons present in hybridized orbital cannot move, cannot go for delocalization. So for delocalization, it prefers to do like this. Take one more example. There is nitrogen. There is lone pair, just like the negative charge, lone pair is there. NS3, you know, hybridization is sp3. Here also, this orbital, and that orbital, and this one, lone pair. With the lone pair, its hybridization is sp3. This one is sp3. But if we keep the double bond, yes, its hybridization is changed. And H, now the lone pair is there. This lone pair is now present in unhybridized orbital. It is changing its hybridization. This nitrogen is now sp2 hybridized. Because adjacent carbon atom is sp2. Very important one. So in that way, here, if the question is number of pi electrons, a very important one these days for integer answer type of question, right? How many pi electrons? Pi electrons here, 0. How many pi electrons? Pi electrons, 2 here, 2 there, 4. How many pi electrons? 2 to 4 to 6. How many pi electrons? 0. How many pi electrons? 0. How many pi electrons? 2 to 4 to 6. 6 pi electrons. So what are the pi electrons? Electrons present in unhybridized orbitals, and that's why 2 to 4 to 6, because its hybridization is sp2, one of the orbital which contains this electron pair is basically unhybridized one, and that electron pair is considered pi electrons, and that's why 2 to 4 to 6 pi electrons. I hope you got it. Now in this context you have to understand that pi orbital having 2 electrons, this is the case of carbanium. And so let's take the same example. CH2 double bond, there the CH and there the CH2 minus. Here resonance can take place. This electron pair is present, is basically there the pi electron pair, and this one is moving here. This will go there. As a result of this, you write CH2, their negative charge no, and there the CH double bond CH2. Yes, that is this. That is delocalized. Now, just summarize. We have discussed here delocalization, various types of delocalization. Delocalization of pi electrons with the pi bond, delocalization of pi bonded electrons with the pi bond, delocalization of pi bonded electrons with pi orbital having no electrons, delocalization of pi bonded electrons with pi orbital having 1 electron, delocalization of pi electrons, pi bonded electrons with pi orbital having 2 electrons. All resonance delocalized will come under this category. Resonance means delocalization of pi electrons, and these are the various types of delocalization. Here, in this context, few things I have to add, because we should not rush to those known terms, right? We should step-wise, we should understand, right? So here, the very first, you need to be familiar with the real process. You have seen that, yes, this is delocalized. Now I come to the point here, that what is the other phase of resonance and how you will see the resonance. Here, resonance, whatever we have discussed, now I just redefined with few other words, right now. I say that resonance is a phenomenon. Is a phenomenon. We will say that resonance is a phenomenon of expressing a molecule with different electronic arrangements. Different electronic arrangements. Yes. Resonance is a phenomenon of expressing a molecule with different electronic arrangements. Here what you have to notice that what I have written, that you see different electronic arrangements. Different electronic arrangements. What are the different electronic arrangements? Yes, we had written that CH2 double bond CH2 plus, and then we have moved from here to there. Oh, those are the different electronic arrangements. Different electronic arrangements. Not different atomic arrangements. Here, if you say different for a molecule, different atomic arrangements means different atomic arrangements, isomers. Those different atomic arrangements for the same molecule. If you have the different kind of, so molecule means molecular formula, not molecule, because every different electronic atomic arrangement means different molecule, right? So for the same molecular formula, if you write the different atomic arrangements, those are the isomers. But when you write here the different electronic arrangements, so those different electronic arrangements are called resonating structure. Resonating structure. You also say canonical structure. Canonical structure. You also say this one contributing structure. Contributing structure. These are the various terms used. Resonating structure, canonical structure, contributing structure, all these, the different electronic arrangements. You see, for example, if I say here that let's write here, this one is benzene, the most known or the most widely used example on the name of resonance is benzene, right? As we did earlier, I try to write here the various electronic arrangements. I break here this one bond and write like this. This one is accumulation of electron, right? And as a result of this, what we write? We write here, there we write negative charge, here we write the positive charge, and remaining things you see, double bond there, double bond as it is. But again, what we write? Here, pi bonded electrons come here in between these two. In between these two, shifting here. How it can shift? Because this one is sp2. It can accommodate. And as a result of this, what we write? As a result of this, now this pi bonded electrons will be there in between this carbon atom and that carbon atom. And what about this? This will be having positive charge because that is losing electrons. And we write here. Now we write double bond here. There as it is, negative charge. This positive charge is no more there. Yes. What about this carbon? Yes, positive charge comes to this place now. Double bond as it is. What next? Yes, now positive charge there. So again this will be moving. Here, that is coming in between these two positive charges there. So as a result of this, what do we write? you write here now, as it is this double bond. This double bond is shifting now to this place. No more positive charge. This negative charge as it is, positive charge is here now. Next, yes. This one is also pi orbital, that is also pi orbital, and here the electrons are given from this orbital to that one. And as a result of this, what do you write? You write here, there double bond, here double bond. I'm now trying to see this one, this structure in this one. You observe that if you mark here, this is 1, this one 2, this one 3, this one 4, this one 5, this one 6. In between 1 and 2 double bond, in between 3 and 4 double bond, in between 5 and 6. But now you will find that alternative arrangement that is changed. Now in between 1 and 2 single bond, in between 3 and 4 instead of double bond there is single bond, in between the 5 and 6 instead of the double bond there is single bond, changing its place. You can express this one directly like this. This one is coming to this place, this one is coming here, this one is going there, and that keeps on going. Same thing you can express here also. There, again here, again there. All these are the different electronic arrangement. This one is also different electronic arrangement, this one also, this one also, this one also, this one also. All these are resonating structures, canonical structures, contributing structures. Sir, why called contributing structures? Because we cannot say the benzene is this one. This is also one of the possibility. This one also, this one also, this one also. All these are the various possibility. Now, so if this is, whenever this will be there, that will also be contributing. This is also contributing its own properties to the actual molecule. This also, this also, this. All those various electronic arrangements, what we say, resonating structures or canonical structures, contribute their own properties as per the properties to the actual molecule, right? And that is different from all these. These are called resonating structures. In this phenomenon of expressing various electronic arrangements, this is resonance. This is resonance. I hope you got it. And here one point which is very noticeable, that with the different electronic arrangements we get resonating structures. With the different atomic arrangements we get here isomers. I hope you got it. Okay. Now we will discuss there how do we write, what is the significance of resonating structures, and what is the significance of the actual one. What do you mean by the actual one? Actual one means when there is continuous process of shifting of electrons in such molecules, then you can write here one of the structure like this also. You can write like this. What does it mean? It means electrons keep on moving. But this is not a valid structure, right? As per that rules of writing various structures, this one is not valid. This is one of the invalid structure. But this is representing the actual molecule. And this is called resonance hybrid. This is called resonance hybrid. So one thing you understand, that the resonance hybrid represents actual molecule. although there is no scope of writing on this paper, on this board, such molecules because it violates all the rules of writing structure, chemical structure. Here, you can write these structures, but none of these represent actual one. All these are hypothetical structures. Actual molecule is different, right? These are resonating structures. Yes, we'll move to the next class. Next one, right? We'll see.